Hey everyone, welcome to KT Semicon Self-Paced Learning Module. In this particular session, let us try to understand how to perform addition and subtraction using ones and twos complement. Before that, let me share my screen now. So in this particular session, let us try to understand how to perform ones and twos how to perform addition and subtraction using ones and twos complement. So basically, let us take a simple example. Let's say if we are going to take two numbers, let me write it down. Let's say if I'm going to take 5 and 7, okay? And let's say if I want to add these two numbers, 7 plus 5, okay? Then let's see how we are going to add it using one's complement form of addition. Now, if you are going to perform one's complement form of addition, then you are going to take your numbers as it is without performing any complement. So for plus 5, for representing this plus 5 in one's complement format, we are going to represent it as it is without performing any one's complement. And on plus 7 also, we are not going to perform any one's complement, we are going to represent as it is. That is, it is represented as 0, triple 1. Now, if we are going to add these two numbers, that is 0, 1, 0, 1 and 0, triple 1, then we are simply going to get 1, 1, 0, 1, 1, 1, 0, 1, triple 1 is 1 and 1, and we are going to get this as our result, which is nothing but decimal number 12. So this is how we are going to perform one's complement addition on two positive numbers. Now, let's say if I want to add plus 5 and minus 7, if I want to perform this particular addition, then using one's complement form of addition, using one's complement addition, using one's complement form, if I want to add this plus 5 and minus 7, let us try to understand how to perform this addition. Now, so plus 5, the positive number, we can represent it as it is. That is, in its true original form, we can represent the positive number. Now, coming to the negative number, we are going to apply the ones complement on this original format. That means plus 7 is basically represented as 0, 1, 1 and 1. And minus 7 if I want to represent. So how I am going to represent it? I am going to apply ones complement on this number. That is nothing but 0, 0, 0 and 1. So this is a ones complement format of minus 7, that is nothing but 1, triple 0. Now I am going to add this two numbers. So how to add these two numbers we already know. So 1 plus 0 is 1, 0, 1 and 1. So this is what we are getting if we are going to add plus 5 and minus 7. So here we can see we are not getting any carry. Okay, here we are not getting any carry. That means if we are not getting any carry, that means our resultant is a negative number. This is a very important conclusion here. If we are not getting any carry, if no carry, then the resultant is a negative number. Now, if the resultant is a negative number for and it is a negative number, now what we should do is if we are not getting any carry, we are going to perform complement on this number again for knowing the actual value. Now, what is the complement on this number? That is nothing but 0, 0, 1, 0, and it is nothing but minus 2. Since we have already seen that, right? So it is a negative number, so that's why we are keeping minus. Okay, so that is what we have written over here. In the case of ones complement addition or subtraction, we are going to write down the ones complement of this upper hand, that is whatever the number which is having a negative sign, that is nothing but our subtrahend, and then we are going to add the ones complement subtrahend with the minuend. Now, if the resultant has a carryover, then add the carryover in the least significant bit, and the number is positive. The number is positive. And if there is no carryover, like this example which we have seen, then the number is a negative number, and we need to take the ones complement of the resultant, and the number is a negative number. Now, let us see one more example and let us try to understand. Let's say if I am going to have 7 minus 5, if I need to perform 7 minus 5. Now, for representing my 7, I am going to simply write down 0, triple 1, and 5 is nothing but 0, 1, 0, 1. Now, one's complement on this 5 is nothing but 1, 0, 1, 0. And if I'm going to add these two numbers, then what I'm going to get 1, 1 plus 0 is 1, 1 plus 1 is 0 and 1, 1 plus 1 0 and 1. I'm going to get a carry. Now, if I get a carry like this, then what should I do? I should add this carry to the LSB position. So what I'm going to get, this is my resultant 0, 0, 0, 1, and I'm going to add plus 1, which was a carry previously. So what I'm going to get, 1 plus 1 is 0, 1, 1, 0, 0. This is my resultant. That is nothing but plus 2, and the resultant is a positive number. So this is how we are going to perform one's complement addition subtraction. Similarly, if I am going to perform subtraction using 2's complement, then what is the process which I am going to follow is, first I need to find the 2's complement of the subtrahend, that is whichever the number which is having minus sign, that particular number. Then we are going to add minuend, that is a, to the subtrahend, and if the final carry is 1, then it is dropped and the resultant is positive. Here in the case of 2's complement, if we are getting any carry, then we are going to just leave it. But in the case of 1's complement, if we are getting a carry, we are not going to discard it, we are going to add it with the original number. But here in the case of 2's complement, we are getting any carry, we are just discarding it, and the number is treated as positive. But if we are not getting a carry, then the resultant is a negative number, and the 2's complement should be performed on the final sum to get the actual value. For example, let's see one example. Let's say if I'm going to add 7 minus 5, if I'm going to subtract this 7 minus 5. Now, 7 is written as it is, that is 0, triple 1. And coming to my minus 5, so 5 is normally written as 0, 1, 0, 1. Now, what is minus 5? Apply the 2's complement directly. So we have 1 over here, we are going to write down as it is. And we have 0, what we are going to do, 1's complement. And this is nothing but 0 and 1. This is the 2's complement of the number minus 1. And we are going to add this. What we are going to get, 1 plus 1 is 0, 1, triple 1, 0, 1, 0, and we are getting a carry. Now, if we get a carry, then the number is a positive number. So, and we can just discard this particular carry. Now, so if we discard this carry, that means our number is nothing but plus 2. So, this is how we are going to perform 2's complement subtraction. Now, let's say if I want to perform a subtraction minus 4 plus 3 using 2's complement form of subtraction, 2's complement form, I need to perform a particular subtraction. Now, the positive number is as it is represented without applying any complement. So, this plus 3 is basically written as 0, 0, 1, 1. And coming to this minus 4, I need to apply the 2's complement on this 4. So, how to apply this 2's complement on this 4? So, first of all, we will write this 4 as it is, that is 0, 1, 0, 0. And we are going to apply the direct method for performing the 2's complement, that is nothing but, so until and unless we find 1, we are not going to perform any complement. And if we have found 1, then we are going to complement from the adjacent bit. That is nothing but 1100. So this is nothing but my 2's complement of my negative number. So minus 4 is basically written as 1100. And we are going to simply add these two numbers. So we are going to get 1, 1, 1, and 1. And if you can observe here, we are not getting any carry. So that means our resultant is a negative number. So what are we going to do is, we are also going to perform the 2's complement on this number. So how to perform the 2's complement? Again, we are going to perform the 2's complement. So that is nothing but 1 and 0, 0, 0. So it is nothing but 0001. Now, the number is a negative number, so we are going to keep minus 1. So this is how we are going to perform 2's complement on a given number. So that's about subtraction and addition of using 1's and 2's complement. And in our next session, we are going to see another topics like BCD addition and so. Yeah, thank you for watching this session. Hello all, welcome to KT Semicon self-based learning module. Now, in this particular session, we are going to discuss about Excess-3 code in detail. Now, the Excess-3 code for a given decimal number is determined by adding 3 to each decimal digit in a given number and then replacing each digit of the newly formed decimal number by its 4-bit binary equivalent. Now, what does this mean? Let's say if I'm going to have a number decimal number 0. Now, so first of all, I need to represent it in BCD format. That is nothing but 4 zeros, and I'm going to add plus 3. That is nothing but 0011. This is nothing but my Excess-3 representation of the decimal digit 0. Now, if I want to represent 1, then that is nothing. This is nothing but my Excess-3 representation, Excess-3 code. Now, if I want to represent 1, then I need to first of all represent this number in BCD format, that is 0001, and I need to add plus 3, that is nothing but 0100. Okay, this is the Excess-3 code. Now, let's say if I'm going to have 2, then how to represent this in BCD format 0010 and adding plus 3, which is nothing but 5. And let me write down for the other things also, 0011 and plus 3. So this is 2 plus 3 5, and 3 plus 3, that is nothing but 6, and 4 is nothing but 0100 plus 3 if we are going to do, it is nothing but 0111, and 5 is nothing but 0101, and plus 3 if we are going to do, it is nothing but 8 1000, and 6, it is nothing but 6 plus 3 is 9 1001, and 7, it is nothing but 0311, and plus 3 is nothing but 1010, and 8 is nothing but 1000, plus 3 if you are going to add 1011, and the 9 is nothing but 1001, and which is nothing but 1100. That's it. So up to here we will complete our BCD numbers. Up to only 9 we can represent. Now these are our Excess-3 code representations of all the numbers which we have written. Now let's say if I want to find out the Excess-3 code for 12, then I cannot simply write 1100 and add plus 3 to it. No, I cannot write. First of all, I need to represent my 12 in BCD format as 0001 and 0010. Then I need to add plus 3 to both the digits, and I'm going to get my resultant. That is Excess-3 code. Okay, so this I need to follow. Now, so this is nothing but my Excess-3 code representation of a particular decimal number. Now, this Excess-3 code is also known as self-complementing code. Now, why do you call this Excess-3 code as self-complementing code? If we can able to see here, let's say if I want to perform 9's complement on a number 0. Let's say if I want to perform 9's complement of 0, then that is nothing but my 9. So you can see over here, 9 is nothing but, in Excess-3 code representation, it is nothing but 1100. Now, instead of performing 9's complement on this decimal digit 0, what I can do is I can just perform 1's complement on the Excess-3 code of decimal digit 0. That means if I simply perform 1's complement on the Excess-3 code representation of 0, if I'm just going to perform 1's complement, then what I'm going to get 1100. That is nothing but Excess-3 code of 9, which is nothing but Excess-3 code of decimal digit 9. That means instead of performing 9's complement on a decimal digit, what I can do is I can simply perform 1's complement on the Excess-3 code of a decimal digit. Then I'm going to get its 9's complement. Okay, so that's why it is known as self-complementing codes. Now let us try to understand what do you mean by gray code. So gray code is a 4-bit numeric code, and it is a unit distance code because successive code words in this code differ by only 1-bit position. And it is also known as a reflective code, that is both reflective and unit distance. So this is how your gray codes are going to look like. For 0, this is your decimal digit 0 and this is your gray code. And for 1, you are going to have this as your gray code. And for 2, this is your gray code. And for 3, this is your gray code, and so on. Okay. So you can see over here, this two adjacent digits, there is only one bit change, right? And between this 1 and 2, if you carefully observe, there is only one bit change. Only this 0 is getting changed to 1. That's it. No other bit is changing. No other bit is changing. Only this 0 to 1 transition is happening. Now, if you observe this 2 and 3, only this LSB bit, that is 1 to 0, is getting changed and no other bit is getting changed. Okay. And you can see any adjacent bits or any adjacent decimal digits in the gray format, you can see only one bit is getting changed. So that's why it is known as unit distance code. So that is the reason it is also called as unit distance code. This is the reason we are calling this gray code as a unit distance code. Now, why this code is called as a reflective code? The reason for this is nothing but, if you can see carefully over here, so up to this particular format, that is 0, 0, 0, 1, 1, 1 and 1, 0, this is one set. And if you treat this line as a mirror, then you can see there is an exact reflection of this sequence over the second format, that is 1, 0, 1, 1, 0, 1 and 0, 0. So this is the reason this gray code is called as a self-reflective code. Here also you can see 0, 0, 0, 1, 1, 1 and 1, 0. If you treat this as a sequence and the middle one as a mirror, then you can see the exact reflection over here. 1, 0, 1, 1, 0, 1 and 0, 0. So that's why this particular gray code is also called as a reflective code. Now, so as we have already discussed, only a single bit is going to change in the case of your gray code, and it is a non-weighted code. Now, for example, in the case of your binary code like your 8421 code, let's say if I'm going to write down any number as 1011, then you can get the value of this binary number by applying the weights 8, 4 to 1, and whatever the weight we have 1, we are going to add it up. That is nothing but 8 plus 2, 10 plus 1, 11. That is nothing but B. That means this particular binary code or 8, 4 to 1 is a weighted code. But whereas your gray code and Excess-3 code are non-weighted codes. What do you mean by non-weighted codes? You can see over here, let's say if you are going to take a Greek code, let's say if you are going to take 1101, if you are going to take a Greek code as 1101, then you cannot simply apply 8421 and you cannot give the value as 8 plus 4, 12 plus 1, 13. No, this is not you're not going to follow for finding out the value, because you can see 1101 is not 13, it's 9 in decimal format. So gray code is a non-weighted code. Your digits are not going to have any weight. Okay. Now, so that is what it is written here. Unlike binary or BCD codes, gray code are not having any positional weights. Now let us try to understand how we are going to perform binary to gray code conversion. Let's say if we are going to have any binary number, then if I want to convert it into gray code, then I'm going to first of all copy the MSB as it is. Next, I'm going to perform the XOR operation between the adjacent bits and I'm going to get the next value. Okay. Next, I'm going to perform the XOR between these bits and I'm going to get this value. Next, I'm going to perform the XOR operation between these two bits and I'm going to get this value. And next, I'm going to perform the XOR operation between these two bits and I'm going to get these values. So this is how I'm going to perform the binary to gray code conversion. Now let's say if I'm having any gray code and if I want to convert it into binary. Now how to convert this into binary? So again, I'm going to take the gray code and the MSB is written as it is, 1 is written as it is. Now I'm going to perform the XOR operation between the first result and the next gray number, and that resultant I'm going to write it in the binary. So in the crisscross manner, I'm going to perform the XOR operation for getting my binary equivalent of a gray code. So this is how I'm going to convert from binary to gray and gray to binary. So that's about this particular session. Thank you.